what we're essentially going to be doing is, this is me practicing. We're essentially going to be deriving Broyden's method as iterative refinement of an approximate Jacobian. So we're going to prove that it is correct for finding the root of a complex computational method. It's a much better way than using Newton's method, because Newton's method could be very long, tedious, and it just Broyden's method is way more efficient. We're going to prove the concept that the above equation over here, we're going to prove Broyden suggests the current estimate Jacobian matrix of Jacobian of n-1, and proving it by taking the solution to the sequent equation that has minimal modification. So Jacobian of n equals to the Jacobian n-1 of all this. We have multiple equations that we are also going to be kind of utilizing and implementing in a certain way to get what we need to go. So let me get a new page, put it on here. Is that picture? Okay, cool, we can see it. So what we're gonna be doing, just gonna make sure it's recording. Cool. Okay, put this back so you can see me in my iPad. So let me see if you guys can see. Yeah, you guys can see very well. Okay, so basically what we're going to be doing is the function of n of the first guess plus the Jacobian of n, xn plus 1 minus the next guess minus the first guess is equal to 0. We're also going to be implementing the function of xn plus 1. We're going to say that is equal to f of x of n, and the Jacobian of n plus 1, xn plus 1 minus the next guess, first guess. And if we're able to subtract that, we can see that we are left with fn plus 1 is equal to j, the Jacobian of n plus 1 is the second guess minus the first guess, and then we can multiply by the xn plus 1. So we're going to say this is the second, I don't want to use numbers. This is the second guess, and this is the first guess. So that the change in the second guess, the next guess, multiplied by the u is equal to 0. So we are saying that the dot product, we're saying that because the dot product is perpendicular, u is perpendicular to the change in the next guess. And then we can also say that we can also say that j, Jacobian of n plus 1 minus the Jacobian of n of u is equal to 0. We can say that because u is perpendicular to delta x in this scenario. So we can get that delta x is equal to u, j, the Jacobian of n plus 1 minus j, Jacobian of n, u is equal to f, the function of n plus 1. And we can use all of this mathematically with what Broyden actually gave us. It was a helpful way of figuring this out. is we need the function of n plus 1 over the change in the x of the transpose, delta x multiplied delta x. And essentially, with setting these equal to each other, we can find this overall expression, which is I'm going to do right now. We can say that j n plus 1 Jacobian of n plus 1 of Jacobian of n over the function of n plus 1 the delta change and the x of n to transpose plus 1 over the magnitude of delta x squared. Okay. Okay. Let's move this up a little bit. And then from there, we can move around some terms and we can see that Jacobian of n is equal to jn minus 1. See how this was plus, now it's minus, now this will change as well. And then we add that to the change in the function of n minus j n minus 1, change in x n multiplied by delta x of n of the transpose all over the magnitude squared. Of x of n squared. Sorry about that. So now that we found this, we can see that the term of the function of n plus 1 of the change of n f of n plus 1 minus the Jacobian of n multiplied that change in x, the next guess, we can see that that will essentially f the function of n plus 1 minus the function of n minus f of n. And essentially what we're left with is the function of n plus 1 is equal to the function of n plus 1. From there, we are also able to derive Broyden's method as an iterative refinement of an approximate Jacobian.